and sublinear algorithms with landmark results on various graph and distributional property testers, and having laid down many of the foundations model of the field. And she's also introduced some central problems in Boolean function property testing, such as junta testing. She's before that worked on learning theory. And in fact, one of the early papers, which people don't in this crowd might not even know, is in something completely different, like error correction based on Chinese remainder theorems. And I personally was extremely lucky to work with her when she was a postdoc at MIT. And I know from first-hand experience why she's such a revered advisor by her students who were lucky enough to work with her. And I think many of them are here today. So welcome, Dana, and we look forward to hearing your talk. And happy birthday.
Okay, thanks a lot. So thanks a lot for the invitation and for the introduction. And I'm really sorry that I am not able to make it to be there in person. But hopefully you'll be tolerant to my virtual image that you can see. So I think I can hear you guys, but if there might be questions, I might not hear. Oh, now I can also see. Excellent. So see at least from a side view. So I'll just go ahead, and you can try and stop me, or you can ask Flema to stop me, and we'll see. We'll try to kind of maintain something interactive as possible. So before I start with this talk, I'll kind of steal half a minute from it to be able to. I wasn't able to say yesterday thank you to everybody for the great day yesterday. To the organizers, to the speakers, and of course to the singers, songwriters. That was really great. So thanks a lot. So now I'll go ahead with the talk. So let's start with property testing. Probably most of you know of it, but I don't want to assume anything in this talk, because I don't know kind of there's other people in the audience, so I'll just try to define everything. So I'll start with, I'm going to talk about tolerant testing, but first I need to talk about standard testing. So we have some fixed property P, we have an object O represented by this blue blob, and the algorithm is given query access to the object and gives it a parameter epsilon. And it needs to determine whether the object has the property or is epsilon far from the property, meaning for any object in the property, and has to do this with high constant success probability. That's this WHCP. And unless I say otherwise, I'm talking about two-sided error, so the algorithm is allowed to err in both directions. And what we aim for is query complexity that is sublinear in the size of the object, and to have low dependence on this distance or error parameter epsilon, hopefully to have polynomial dependence on 1 over epsilon. So in order, of course, to define a problem precisely, I'll have to say, what is the object I'm talking about? What is the property? What exactly is the axis that I have? And what is the distance measure? So whenever I'll talk about something, I'll try and be as precise as possible. And if you have questions about anything about these 4 things or anything else, then just stop me. Okay, so this was standard property testing, and so it's visualized at this. So this is the property, the set of objects that have the property, and we need to determine whether the object is in this set, belongs to the property, or whether it is outside the epsilon far. So this is the standard notion. Turning to the tolerant, what you've heard about already yesterday, some of you. We need to determine, so again, we have this property P, we have this set. We need to determine whether the object is now epsilon 1 close. So this is the green is the color code for good. So it's epsilon close to P, or if it is, that's a good case, or if it is epsilon 2 far from P. And ideally, we would like to do it for every epsilon 1 smaller than epsilon 2. And then we want a low, hopefully polynomial dependence on 1 over the difference between them. But in some cases, we're going to allow, or just that's what we'll be able to do, get some results with constraints. Say, epsilon 2 is just 2 epsilon 1, or 2 epsilon 1 plus something. And the third notion is distance approximation. So here again, that's a property. And we want to obtain an estimate of the distance of the object from the property. And again, this may vary what we mean by distance approximation, particularly say an additive distance delta and with low polynomial dependence on one over delta. I want to say something about these drawings. So I listened to Rocco's talk, who also gave a talk a few weeks ago, and he said, that everybody is using Clément's egg drawing. And I say, no, is this really an egg drawing? I'm not really sure. The proportions are not exactly right, so I'm not doing the right thing. And then I just decided to myself that I have this as my vegan egg, so then it's okay. So hopefully Clément will also approve of this notion. So these are the three things here. I just wrote them kind of shortly: standard, tolerant, and distance approximation. So one thing that kind of you can see that the very distance approximation, tolerant testing kind of are essentially the same. So again, it depends on what I mean exactly by distance approximation, what exactly I mean by tolerant probability testing. But definitely, if I can obtain an additive error, so go to that definition, additive error of delta for any delta, then I can get a tolerant property testing. I'll just set delta to be epsilon2 minus epsilon1 divided by 2, and I'll be able to compute. In the other direction, you need to work a little bit harder, but you do some type of search, and you can get, so basically here, I'll use the two notions interchangeably, and the kind of my choice of which one to use will depend on the work that I'm presenting, and then according to how it was presented in that in the paper. But you can think of these two things as there are subtleties, but you can think of them as being the same. So one thing that you might guess, or again, if you were yesterday, and then you already know, sometimes tolerant testing is much harder than standard probability testing. So it was first shown by Fisher and Fortnow, and then was later strengthened by Benelez and Fisher, Levy, and Rothblum. And there are also other separation results, which I'll mention later. In particular, it will relate to a question that was asked yesterday. But these were I'll start with this. So it can be much harder. But sometimes, it's not harder, or at least it's not much harder, or at least it's not too much harder. So that's where I'm kind of that's where I'm interested. And one thing to note, again, general type of thing to note here is that if I have a standard tester whose queries are uniformly distributed, so each query on its own is uniformly distributed, not necessarily independently, then we can get some type of weak tolerance. So I can get for any epsilon2, I get epsilon1 is 1 over the query complexity of the tester. And so this is kind of a baseline. But first, not all testers are of this form, and also if they are, I want something stronger. So here in this talk, I'm going to focus again. I'm going to be in a positive mode. I'm going to focus on positive results, and I'm going to describe several algorithms in different domains, and to give you just a taste of things. So kind of the structure of the talk will be, it'll have 3 parts. And already I'll say, if I get to the third part and I see that over time, I'll do what I can get to. But the idea is really to give you kind of a taste of some specific results. And then around each specific result, I'll give a bit of more context of other related works. And also the taste will be either, small teaspoon or larger one, depending on kind of on the result itself. Okay, so this is where I'm going at. So I'll just before I kind of jump to the first problem, are there any questions about the notions themselves, about the problems themselves, about these notions of tolerant and distance approximation? Okay, so let's go ahead. So the first problem that I want to talk about is, well, again, you've heard about it, is monotonicity. In different contexts, you've heard about it. So let's see, what do I mean here at this point by monotonicity? So I have a function from the integers 1 to n to some fully ordered set. Say it's the reals. And I say that it's monotone, non-decreasing, if f of I is upper bounded by f of j for every I less than j. Okay? And so, for example, here, this is how I represent it. I kind of by an array, I'll represent the function. So this is a monotone function. But this one is not, it starts going up, but then it goes down, and then it goes up and it goes down. So this one is not monotone. So there are actually several standard testing algorithms for this, for the same property. There's several algorithms. And so just to make sure, what I said, I have to be precise when I talk about the problem. So they have query access to the function. They can ask, what is f on any point I between 1 and n. And they need to decide whether the function is monotone or it's epsilon far. And what is the distance measure? It's going to be just the normalized Hamming distance. So it's the fraction of points that we need to modify in order to make this the function monotone. So for example, here, if I compute it correctly, hopefully, this is 2/5 far. So we need to modify 4 points out of the 10. And I'll just say that there are also, it's been studied also according to other LP norms. So, but this is the type of, this is the measure that I'll be interested in here. So kind of think of it that, you have this, you measure something physical, and you kind of, you want to say, kind of think there may be a small number of outliers, and you want to tell if actually, it's nicely monotone, there are many outliers. So this is the idea. So the query complexity, said there are several algorithms. The query complexity is goes like log n over epsilon. So it's can be a little bit better. And I'm choosing my favorite. So I said there are several, even in this paper of Ergun, Kanan, Kumar, Rubinfeld, Viswanathan. There's more than one algorithm. They're also in other places. So this is the one I like most, because I like describing it. I like presenting it. So let's see what it does. And I'm going to assume here that the values of f are distinct, and this can be made, this assumption, without loss of generality. And you can think about it, or kind of peek into the paper and see why that's true. Okay, so what does the algorithm do? So it selects uniformly independently at random a sample of indices, something like 1 over epsilon indices, 2 over epsilon, and I'll denote them I1 through Ix. What does it do with them? For each of them, it goes, now it queries the function. Until now, it didn't perform queries. It queries the function on each of them, and it kind of sets for each IR, say x of r is the value of the function. And then it kind of forgets where it was. Well, it doesn't really forget. It puts this on the side. But it then performs a binary search on f. So viewing f as an array, it performs a binary search for xr. And if for any xr, the binary search failed to return the right index, then we reject, and otherwise we accept. So the easy thing to see is that if it is monotone, binary search works when something is sorted, so of course. And the harder part is showing that if it's epsilon far, then really we will reject with high constant probability. And I also had an animation for running the algorithm. I decided, no, I don't have enough time. So if you can just run it on your own and see and get a feel of when it rejects. So this was just to give you kind of the context of the standard tester. Now we're going to, so this is the standard tester. And now we want to make things, more tolerant. So we're a distance approximation, want to approximate the distance. So a naive idea to modify this into a distance approximation algorithm is just to say, okay, no, you'll do kind of the same, maybe take a larger sample, and then compute the fraction of sampled indices on which the search failed. Well, it sounds kind of like a natural thing to do. There are cases in which it works. So one of them is actually an example that is used in lots of contexts. So what I did here, that I took something sorted, and then I kind of swapped every pair, every consecutive pair. I swapped them. And here the distance, I'll tell you, and you believe me, that the distance is 1/2. And indeed, on 1/2 of the indices, so this really will work here. But it's not a good idea in general. And so take for this example. So this is really almost monotone, almost perfect, except for this annoying 100, which actually sits right in the middle. And in terms of the distance, I just have to modify it, and I'll be fine. But if I run the algorithm, it will, even though it's very close, I will get on half of the indices. I'll fail to find them because of this one thing. So we can't use this naive idea, but it's good, to start and thinking about naive ideas. So so I mentioned one thing that I had my rule here of references. So something this is not yet Ronit's a birthday party, but still I will say many things I've learned from Ronit is one of them is to try and actually use full names in references. So it's good, people can see them, but then I do it only once. So from that point on, you have to, because this is Parnas, Ron and Rubinfeld. And what we, in that paper, which we started talking about tolerant testing, we gave a tolerant testing algorithm. It worked for epsilon 2 that is 2 epsilon 1. I said sometimes I allow different types of tolerance plus delta. And the query complexity was polynomial in log n over delta. Okay, so I'm going to give you here, just in this slide, something, again, I said, a flavor, just something about the idea. And some of this idea is actually, it takes things from previous work. So one of the things also, when I listen to work, sometimes what I learn is what happened before actually the new result, whatever that people are talking about. And that's good enough. So the rough idea here is to approximate the distance homogeneity by approximating the size of a maximum matching in the violation graph. Okay, so I'll have to say what I mean by violation graph here and why maximum matching. So what will be the violation graph of the function? So I'm going to have a vertex for every index or every function value. And I'm going to put an edge between every pair that violate monotonicity, but are not in the right order. So I think hopefully I drew here all the edges. So 20 is bigger than 110. That's not good. 40 is bigger than 30. So these are the edges of the violation graph. Okay, so n vertices and an edge for each pair that violate. And why maximum matching? Because the distance homogeneity, it's not hard, and this is actually for general posits, distance homogeneity equals exactly the minimum size of a vertex cover. And well, we're not sure how to compute the vertex cover, how to approximate it, how to compute it exactly. So we approximate it using maximum matching, and this is where the factor of 2 comes from. So this is the first idea. Now comes the second idea. So suppose I knew the median value of the function f. So the median value, it should be in the middle. And then what I have is that I will have a perfect matching in this violation graph between the indices before in locations 1 through n over 2 that are above the median, and those that are from n over 2 plus 1 that are smaller or equal to the median. So I will have a perfect matching between them in the violation graph. These are not on the right side, and there are the same number of them that are not on the right side. So here, for example, here in this particular example, there's just one edge crossing. So of course, there's a perfect matching between here, but this is something true in general. Okay, so this is a good starting point. So, and then the remaining edges in the violation graph are either on one side or on the other side. So, if I can compute a maximum matching for just those that violate, that go kind of cross this cut, and then I can continue recursively. So I would like to continue recursively, but few things to note. So first, when I continue recursively, I have to be careful not to match points that are already matched before, kind of on higher levels of the recursion. And I need to compute medians on yet and match points. So something here kind of we have to work on. It's not immediate, but even if somebody will kind of give me in my ear, will tell me these answers, still I want a sublinear algorithm. That's kind of the whole point. The size of this recursion tree is not sublinear. However, we can overcome these issues. So we can overcome this issue by defining in our head this kind of approximate recursion tree. We call it index value tree, and sampling paths in it. So I'm not expecting you to understand this stuff, but kind of this idea of having this, there is this big thing, and also in other places, sublinear algorithm. There's something in our head, this big thing that we're not actually computing all of it, but we're kind of sampling into it, and having a path allows us consistency, and we don't need too many paths. The paths are in this tree are of a depth log n. So something you can smell that it seems maybe reasonable that will be poly log n over delta. So this is what I'm going to say about this work. Now, and one thing when somebody writes poly, then usually you can expect that it's not linear and probably also not quadratic. It's bigger than that. So in this case, it wasn't not 500, but it was 7. That the exponent on log n. I don't remember on delta. And in follow-up work for Lon Chazelle, Komandura, Liu, they reduce the exponent from 7 to just 1. So they just have really, and I want to actually state the result more precisely because they say it in a different way than we did as a distance approximation, not a tolerance. So I want to be precise in how they state it. So they provide an estimate. Epsilon mon of F is the distance of monotonicity. So it's between epsilon mon and twice plus some constant gamma, and they get up to tildes log n over epsilon mon queries. I'm not sure about the dependence on gamma, so maybe Sesh can say that later. But they get here something really much. The dependence on log n is they really get it just to linear. So that's really cool. But then there was another work of Sesh and Mike Sachs, which they get rid of the factor of 2. So they provide an estimate that really is very, very tight. They do pay for that in complexity, but you have here kind of a choice between getting something very, very tight and with higher complexity, or say factor 2 is good enough for me, and then get something with really nice and low complexity. So are there questions up to now about this? And again, some of the questions might go to Sesh if you want to talk about to ask about the other works. Okay, so at this point, I told you also that I talked about one problem, one result, then I gave you kind of follow-up work. And now let's put this in a little more kind of larger context. So you might ask, what about other domains and ranges? So when people talk about monotonicity, they talk a lot about the Boolean hypercube. And also there are variants, there's uniqueness, K-monotonicity, and there really has been a lot of work. So I wanted to use even larger fonts, but if you say I have these kind of dense slides, so I couldn't afford using larger fonts here. But there's really a lot of work on standard testing of monotonicity, and there's also been quite a bit of work on tolerant testing. So I'm going to tell you just a little bit, in particular for the most well-studied monotonicity over the Boolean hypercube. So, and this also was mentioned already. So there's standard testing. So I use D here and not kind of, I'm going between, should I use N? Usually people use N, but I didn't want to confuse it with the N from before. So D here is the dimension. And so the domain is of size exponential in D. And for standard testing, there was a sequence of works culminating in Karp, Mincer, and Safra, which gave D to the 1/2. A dependence on D on the dimension, and there's for non-adaptive it's tight, and for adaptive there's this gap here. But here we really get very nice for standard testing. We get something really nice. So what about tolerant testing? So here I said one baseline before was for uniform algorithms. Another baseline for tolerant testing algorithms is similar to standard testing, where if you have a learning algorithm, precisely a proper learning algorithm, you can then use it to get a testing algorithm. So kind of learning implies testing, or proper learning implies standard testing. So there's a similar phenomenon for agnostic learning. I won't define it here, so those who are not familiar can check it out. But there's if you can use agnostic learning to get also tolerant testing. But here, if we use agnostic learning, then we get something that's exponential in square root of D. So then you might say, that's an overkill. Why do learning? You just want testing. You just want to know. You want to do just tolerant testing or distance approximation. It's different from actually learning the function. So unfortunately, has been recent work. Maybe fortunately because we learned from it a lot, but unfortunately for us that we want nice polynomial algorithms. So there's recent work of Chen, Li, Nadine Pali, and Servideo, who proved the lower bound in which the exponent is here this is D to the 4th and not 2 to the 1/2, but still it's very high, and also the same dependence here. So it's really kind of, there's a very big difference. Remember we talked about, I mentioned separation, so that was for kind of unnatural PCP-based functions, but there's also here separation for natural functions. But on the positive side, if you're willing for a weaker approximation, if you're willing that the gap between kind of epsilon 1 and epsilon 2, or if you think about that, then you're willing to, for a factor approximation, for some factor approximation. And then there's a work of Palavur, Spinnikova, and Weigert, and they improve on old work of mine with Shahar Fatal. They give a factor. So here now, d to the 1/2, don't confuse it with the d of the complexity here. This is the factor approximation. It's a non-adaptive algorithm, and it uses poly D queries. And my last line here that hopefully you can see, they actually show also a kind of type result for this type of approximation. So what we have here, we have kind of different types of approximations of tolerance. And in one of them, we have an exponential lower bound. And if we are willing to have a bigger gap between epsilon 1 and epsilon 2, or a bigger factor, then actually we can get the poly D algorithm. So this is what I'm going to say about monotonicity, also in the bigger context, and not only for kind of the 1 to n. So questions at this point? Okay, so I'll move along. So those of you, I hope you like monotonicity, but if you prefer graphs, then you can kind of put the monotonicity on the side, and let's go to another property of graphs. So it's a connectivity, and a little bit more I'll say about other graph properties. So when we talk about graphs, the first thing we need to say, well, in general, but in particular in the context of testing, we need to say what the graph model is. There are various graph models, and they have different names. The kind of Talia is angry that I use sometimes different names for the same thing, or the same name for different things. So, but I'll define things here for this talk. I'll be precise. I'll talk about what I'll call the sparse graph model. The graph is represented by incidence lengths of possibly varying lengths of the neighbors of each vertex. And then this kind of says what are the queries. So the queries are who is the ith neighbor of V? That's the type of queries that I can perform. And what about the distance? The distance here is the fraction of edges that should be modified to get the property. More precisely, I'll think of M as an upper bound of the number of edges. So you're given M, upper bound of the number of edges, and you need to and that the distance is with respect to this M. So a comment here to connect again to a talk from yesterday that Aded gave about the bounded degree model. So if we have that the lists are bounded lengths, here remember I didn't, there could be short lists, long lists, but if we have that there are bounded length and the distance measure is d times n, again up to constant factors, maybe the models can vary, then we get the bounded degree model. But here I actually want to talk about allowing different lengths of a number of neighbors. Okay, so I call it sparse because usually because of kind of the queries. Sometimes you want to allow also pair queries. That means like we want about the adjacency. Is there an edge between two? And it makes, if the graph is sparse, this thing makes more sense. I'll talk a little bit about the adjacency makes model today, but for now, this is the model that I'm talking about. Okay. And usually there also one may perform degree queries. Actually, I won't need it here, but this is also usually something that is used. They can replace by kind of doubling. You can approximate. You can find actually the degree, but here actually I won't need it. But this is also standard. Okay, so queries who is the neighbor and the distance with respect to the number of edges or an upper bound on it. Okay, so now again, let's remember where are we? So I defined a model, and I want to talk about connectivity. That's the property. So I said what the object is. I said what the property is. I said what the queries are, and I said what the distance is. And the algorithm should decide whether G is connected or it's far. So here, what does that mean that it's epsilon far? It means that you must add more than epsilon m edges to make it connected. Okay, so this is what is the meaning of testing in this context. And so in work with Aded, where we worked on the bounded degree model, we gave an OTel, the one over epsilon query, one-sided error testing algorithm in the bounded degree model. And then it was adapted with Michal, it was adapted to the sparse graph model. So D average here, again, I don't care about constants here. So D average will be M over N, and assume here that M is at least N minus 1. Otherwise, you know that then it's not connected. And actually, I think it will be helpful to just think about the average degree as being a constant, so you kind of ignore it. I want to keep it because it's part of the result. It actually goes in our favor if the average degree is large, but that is sometimes confusing. So think of it as a constant. Okay, so I'll only talk about that kind of the other parameter. So it was adaptable to the sparse graph model from the bounded degree, and the complexity is something like 1 over epsilon squared. And there has been also follow-up that improves either in general on this result, or in some context for a constant degree. And so this is Berman, Raskolnikova, and Yarostilov, I should just say Gregory, and Poilievre, and Levy, Poilievre, Raskolnikova, and Varma. Okay, so this is, so each kind of result, before I talk about tolerant, I have to tell you what is known about testing. So up till now, I told you what the model is. I told you what is known about standard testing. Okay, very, very efficient, kind of, you can't really kind of hope for more efficient than 1 over epsilon testing. And in this model, it's slightly different. Very polynomial 1 over epsilon. Okay, so so what turns out that we can obtain, remember that in distance approximation, I want delta approximate an additive distance. That's, so one can think of other approximation, but I want an additive distance. So work of Chazelle, Rubinfeld, Trevisan, that actually works on, the work is on approximating the minimum weight of a spanning tree. It's kind of, so that's what they worked on, but it gives in this work that actually solves the problem here of testing connectivity with Pauli 1 over delta queries. Again, let's forget about the D average. But what I want to talk kind of in my taste here, so again, the average is M over N. In my tasting here, I want to actually describe a less efficient, but very, very simple to analyze. So I'll be able to give you even kind of a bigger taste than I gave before, and you'll get a feel. This is work with Sharon Marco, and actually I think I remember that she gave this algorithm independently, but unfortunately later than the Chazelle group Trevisan. But then we had other stuff that I'll mention. So let's see the algorithm, and basically I'll give you also its analysis in this one slide. So let n of v for a vertex v, let n of v be the number of vertices in the connected component of a vertex v. Okay, so say this is the graph. So here these guys get their nv is 2, and these guys it's 4. And another notation is for some integer r, which I'll set in the algorithm. V sub r are all those vertices whose components have size at most r. So if r equals 3, then we'll have here V of r will just include these two guys because these are in a bigger component. Okay, so these are, and I'll keep this here. And if you want me to remind you, just kind of tell me that you want to put your hand up, and then I'll remind you of the notion. But I'll keep them here. Okay, so now this is all I need for defining the algorithm. So I'll uniformly select something like 1 over delta square vertices. And I'm going to set this threshold r to something like 1 over delta. Again, I'm kind of think of the average as constant, so clean it out and forget about the 8 and the 4. And we're very specific here. We don't really need to be that. So this is what we do. So this is what I select this number of vertices, and I set a threshold r, and it'll be a threshold of sizes of components, not of radiuses of them. And now what I'm going to do for each vertex that I sampled, I'm going to perform a BFS. And what I'm going to do is I'm going to either determine the size of the connected component. So if it's small enough, the size of the connected component is of size at most r, then I'll see it and I'll know exactly what is n of v, what is the size of the component of v. Either if I discover that it's bigger than r, I just go one step more than r, then I know that it's not in VR. Okay, so I'm computing precisely for the sampled vertices. I'm computing the size of their components. Condition if they are in components that are not too big. If they're bigger, I just give up. I don't care about them. But if they are, I compute it exactly. And now this is and this is what I do. And I compute this thing. Now, it depends, some people will say, oh, of course, I can see, you just compute this, and this is, of course, it's right. Others, I'm not expecting that you'll see why it's right, but in just a few more lines, I hope that I'll convince you why this expression is really the right expression. So either if you see it already, then you can kind of doze off. But if you don't see, then bear with me, and I'll explain why this is kind of the right thing to do. Okay, so let C of G be the number of connected components in the graph. Okay, that's and the first, we'll just have the sequence of very short observations. First observation, 1, the distance to connectivity, that's epsilon con of G, the distance to connectivity of the graph, is just the number of connected components minus 1, normalized by m. Remember, we said that it's with respect to this upper bound m on the number of edges. Okay, so we have here, it's even simpler than what we had before with the vertex cover. You have to prove something there. Here it's just immediate, that this is the distance to connectivity. Okay, observation 1. Observation 2, if I sum over all vertices in the graph, this value 1 over v, so I sign every vertex kind of has its little token of 1 over the size of its component, and I sum over everybody, then I just get the number of connected components, because within each connected component, each vertex contributes its part. Right? They're kind of equal within their components. So it contributes 1 over the size of the components. So if you sum over each component separately, together they kind of buy their component together. And then if you sum over all vertices, you just get the number of connected components. Okay, so that was the second observation. Now the third one, here again, some people can really kind of see it immediately, but here if not, then just believe me that I set the threshold R so that if I sum only, so this was over all vertices, if I sum over only vertices that belong to V star, I set the threshold in a way that the number of connected components is not too big, and hence that the sum over here, the number of connected components that are of size greater than R is not too big, and hence the sum here is at least the number of connected components minus delta over 2m. So I have here, so what I know, it's definitely at most the number of connected components, and so I have kind of I know that it's very close to the number of connected components. Okay, now after we said these observations, let's go back to this expression over here. Let's first kind of look from the middle out. So we look at the middle here. What do we have? We have the sum over all vertices in the sample that belong to VR, because I don't know about the other ones. 1 over n of v, and then I have this kind of normalization factor of n over s. So this random variable, because I sampled vertices, this random variable from what I wrote down here, these observations, its expected value is between, so it's at most the number of connected components, and it's at least the number of connected components minus this error. So this is the expected value. So now you can already see almost that when I take this and kind of plug it here, the minus 1 is really, well, it's not really needed because we're approximating, but it's to see things here, we're just plugging things here. This is the same 1 over m, this is the same n minus 1. So in expectation, we're doing very well. But now look, so this was said in expectation, we sampled the vertices uniformly at random, right? We took this sample, and we just have these random variables. They sum up to high, but they each one of them is between 0 and 1, and so we finish up by applying Chernoff bound, and we essentially get what we wanted. Okay. And so the more efficient algorithm is slightly more sophisticated. It doesn't go by just a strict threshold. It's neater, but it doesn't fit exactly its whole entire analysis on just one page. So I prefer to get this. So questions about this? Okay, great. So what about other results? So this was connectivity, just kind of maybe the most basic thing that you can think of. So in the same paper, we talked also about k-edge connectivity.
Can you hear us?
Yes, sure. Now I can hear. Yes,
okay,
I'll
so
go back.
Yeah, there was a question.
Yes, great.
Thank you. I was trying to see if, for instance, this kind of argument can be extended to biconnected components, right? For example, your observation 2 is still true, but presumably you don't have a replacement for best first search for biconnected components. Is that the problem?
Okay, so you're talking about higher, say 2 connectivity?
Yeah, 2 connectivity, yes.
Okay, right. So there are also, okay, so there are structures for 2 and higher connectivity that are related. So they're not exactly, they're not exactly like connected components, that it's really nice and clean that you can't get out of them, because you can get out of them, right? By if it's a 2 connectivity, you can get out of them maybe by 1 edge. But then there are different procedures that are not that are based on BFS, but what they try to do roughly is search for small cuts. So I try to find whether I belong to some small cut, and that will, through these type of sampling and computation, I will be able. So there is this underlying bigger structure of this kind of based on cactus trees. In 2 connected modes, it's even simpler, but it's K connectivity. It is, but still there is something analogous a little bit to connected components. It's a bit more complicated, but it is related to approximating small cuts, and via them getting an approximation to K connectivity. So I hope I gave you something
Thank you.
of the idea.
Sorry, I also have a question. You might have mentioned it and I might have missed it, but if you don't know the average degree, can you adaptively guess it, or?
So you're saying if I don't know, if I don't know M, so here I think we'll have the same type of trouble if I'm not given an upper bound on M. And I think we'll have the same type of trouble that I'll have to search, and this will cost me. So I have to think exactly if they're the same type of thing of hiding things, and then in a kind of a small part of the graph, and then we won't be able to do it with this small complexity. But that is what I kind of guess. But I have to think about it a little more. That's a good point. Okay, so any more questions? Okay, so that's what I was saying about other results, and this connects to the question before. So so we extended to K edge connectivity. Again, the structures are more complicated a bit than but still there are combinatorial structures that we can build on. And we had some results for subgraph-freeness, particularly triangle freeness. Again, this is in the sparse graph model. I won't give the details here, just to give you a feeling that there are additional results. I'll also mention that there's work by, I hope I'm pronouncing it, Campagna, Gu, and Rubinfeld. And what I kind of, there's nice, they build on this general, they present local reconstructors, and they base on an observation idea of Zwickabel-Skepsky, that they use them to get tolerant testing. And they also get it for K connectivity, but also for others. So they have like something that kind of connects to tolerant testing. There are also results for restricted classes of graphs. In particular, for say, planar graphs, there are results that kind of it helps that they can be kind of partitioned into small parts with few edges going between them using local partition oracles. And one last thing I'll say about this sparse graph model is that, as Oded mentioned yesterday, there's a large separation result between standard and tolerant testing for bounded degree. And I'm sure here I said, I really didn't cover, I'm sure there are other results. So actually in bounded degree, or in sparse model. So if I ever write, I don't know, a survey, I don't want to say this, then maybe I'll have to do it. So people, please send me if I miss something, because I think also with tolerant tests, sometimes it hides inside another, the title is something else and it hides inside. So I'll be happy if you send me. Okay. So here, so let's see how much. I think I still have enough time to talk, and I think that this is important. So I would talk about graph. So I talked about connectivity specifically, and then I said in the sparse graph model. And then I said, other things in sparse graph model. But then you might ask, much of the work in property testing is about the dense graph model. So what do I mean by that, or that JCC matrix model? So in this model, the graph is represented by an n by a adjacency matrix. And the queries is there an edge between U and V? We call them pair queries. And so it's probing into the matrix. And the distance then is, you can think of it as if M is upper bounded by n squared. So the distance is with respect to n squared. So that's why it's appropriate for dense graphs. So this is the dense graph model, or the JCC matrix model. And much of property testing deals standard with graph properties in this model. So what about tolerant testing? So here, there's a result of Fisher and Newman. They showed that actually every property that has a property testing algorithm that makes a standard one, makes a number of queries that only depends on epsilon, also has a distance approximation, like with additive delta, L, that makes also Q prime just something that depends on delta. So this is pretty cool. The downside is that they can show, since it's a very general result, they can show an upper bound of Q prime of delta is a tower. I actually thought it was a wowzer, and I thought that would be, but then I found that I saw in the Shapiro's paper that actually say it's a tower, so I can't use this wowzer, which is even more dramatic than a tower, but towers are big enough. But then what happened, also recent result of Shapiro, Gishbeliner, they recently proved that Q prime of delta actually can be upper bounded by double exponential. And furthermore, for hereditary properties, the transformation loss here from standard to distance approximation, just a single exponential. And if you are, you say generality is great, but you don't like these exponentiality, then I'll just mention there are also results with polynomial dependence on 1 over delta. One of them dates back to the GGR paper with the Dedded Shafi for K colorability. So that's kind of a nice natural property. It actually goes by approximating. It relates to max cut. And again, the last, I won't talk about this, but with Nimrod Fiat, we also have some other polynomial results for this. So this is what I'm going to say about that dense graph model. So before I go to my very last part, which I'll do maybe not fully, but at least partially, then I'll stop and see if there are other questions here. Okay, so last thing, yes?
Yeah, I have a question. So in the few examples that you did about tolerant testing, it seemed like there's a connection. I mean, in one direction, the connection may be obvious that if you have a tolerant tester, you can actually also find an object which has the property, which is close to your object. So in one direction, I guess, maybe it's obvious, and I'm curious whether that might be true in both directions.
Okay, so let me see. So you're saying, like we have, say, let's say it was.
So like in the dense graphs, you can find a partition or
Okay. So
in time, which is not sublinear, but time which is better.
Okay, so that it implies, you're saying that testing, even though testing is sublinear, that it implies actually finding something that is close.
So I wonder if the fact that you have tolerant tester as well implies something about that. Yeah.
Okay, so I have to think about it. I'm not sure if it's in general true, but that's a good question. This is rated really, it means more, again, I can't do it sublinearly, but you're saying it implies that the analysis, you say, actually implicitly defines something that is close.
That's what I'm asking.
So actually, I'm not really sure if I can, if this is a general phenomenon or it just comes up kind of here in this.
Yeah. Okay.
So
Thanks.
I have to think about it. Thanks. Okay. So I'll write it down. Oh, Dad, write it down for me. Okay. He's busy with something else. He's not listening to me. Okay.
And maybe another question. So it's known that for testing, not tolerant testing, but in the dense graph model, adaptivity doesn't really help by more like a quadratic factor. Is it also the case for the tolerant version, or?
So here in general, I think it will also be, there'll be this just quadratic
Same.
thing. It'll be the same here. Okay, so now I will get to my very last and more exotic flavor. And I'll say what I mean by exotic. And again, I'm saying, yeah, you see, I have like, I know, 7 more minutes, but so I'll use at least part of the time to at least, again, give you just a taste of it. So it's not exotic in terms of the property. The property is really something, you know, that also comes up. It's a natural property. It's simple to define. But the exoticness is more in the model that I'm going to talk about. Why does this? Something went. Okay, okay, so I'm fine. Sorry. So what is, first I'll say the property, then I'll talk about the model. So the property W is a subsequence, which I'll call a word. That's why I'll use W. And T is a sequence, or call it a text. And think of, you know, K is smaller than N, but I'm not thinking of K as a constant. It's I want it as a parameter. And what do I mean that T contains W if W occurs in T, but possibly non-consecutively? Okay, this is, and otherwise, so that means it contains. Otherwise, if it doesn't contain, it's W free. Okay, so example, say W is 1, 3, 2, and this is T here. So this T contains, again non-consecutively, it contains W. So it's not W free, and it even contains it more than once. So it's definitely, it's not W free. On the other hand, this text, and if you look at it quickly, you can actually hear this is one of the things that you can verify. This is W free. So we can't, there is no copy of W of this 1, 3, 2 inside T. So this is the property that I want to test. And now we get to the model. So this is why I'm kind of switching. I allowed queries until now. I talked about always the distance measure was always pretty much, it was normalized Hamming. Now I want to talk about the sample-based. And so in the sample-based model, I cannot query T, but I can get random samples. Now, when I say random, let's see what I mean. So there's a vanilla version of the sample-based, but still nice. I actually kind of like vanilla. So it's a uniform sample-based. I is selected uniformly. And then the distance is the normalized Hamming distance. So distance is similar to what we had before, but we cannot, you know, probe the function. We just get samples. And in the more general distribution-free sample-based model, I is selected according to some arbitrary unknown distribution P, and the distance is determined by P. So it's the weight that we have to modify in order to get. So here, we're actually kind of getting close. You know, we started talking about probability testing, so we thought about the relation with, you know, with the learning. So here, this is kind of the closest we are to what usually people work on in learning. So this is the sample-based and general distribution-free, and this is the property. So any questions about either the definition of the property or what sample-based or what distribution-free is? Okay, great. So if you want to ask it kind of later, you forget something, that's totally fine. Okay, so as I asked before, I kind of say what I know about testing and then what I know tolerant testing, and I might not be able to say how we do it, but at least I'll kind of tell you. So you'll just know a little bit about what we have here. So in the standard sample-based distribution-free, again, get the samples and distribution-free. Then the sample complexity is order K over epsilon. It's a one-sided error algorithm. This is work with a supposing. And it was implied by previous work for the uniform distribution with a higher dependence on K. And we both care about the dependence on K, and we want this distribution-free. And furthermore, this is tight, this complexity for every W. So kind of when we think about lower bounds, the first lower bound, we would think about that, you know, there exists a W for which you must have omega K over epsilon, but this is a stronger lower bound. For every W, there are no easy Ws. For every W, you know, it's enough. This is a sample size, sample complexity is enough, but also it is necessary. So that's what we show. And a comment here, you might ask, before I get to the tolerant, you might ask, okay, so, sample base, that's great, but, you talked about queries all the time. What if I give you queries? Does it turn easy? So also this is interesting, and it follows from other work that that actually, even with queries, one-sided error under the uniform, you cannot do better than K over epsilon. So here, actually, we don't lose from sampling, and might as well do it with sampling. So this was testing. What about tolerant testing? Again, sample-based, distribution-free. So the sample complexity for additive delta is O tilde K squared over delta squared. The 1 over delta squared is necessary. So actually, this is this is with Omil coincident, both parts, the upper and the lower bound. But we don't know that the dependence on K really is necessary, and there might be some kind of, maybe it's not, because for specific cases, again, this K monotonicity that comes up here in this work of Kanon, Grieger, Kumar, and Wimmer, and there's a kind of improvement of work of Abraham Blum and Hu. They can get, for a special case, and here it is distribution free also, they can get actually linear dependence on K. So you need the 1 over delta squared for a particular W, but the question if you can do it for general W. So I think I'll do this this rushing through thing, though there are all these nice animations, because I won't have time to talk about this notion of roll disjoint, and I'll just jump ahead to my last slide of what haven't I talked about. So lots of things. They'll come one after the other. And some of these things, if you want to hear about them, so one of them you have heard Sophia mentioned yesterday, talked about erasure resultant, and actually you can ask Sophia about lots of works here. So both about Lifshitz functions, images, edit distance, so she can cover half of what is written here. About juntas, there are quite a lot of works, and Roku mentioned this also, and talked about this in his talk. So you can go to the recording of that, and there are also other types. So there are kind of more stuff that I haven't covered here, and I'm pretty sure that I didn't even mention everything here. So I think I'll mention here. I see exactly on the spot that it's, and I have your time. I didn't want to be confused, so I said I'll have a little talk here with your time. So I think I'm done, and I'll be happy to answer any questions that you have.
And very nice overview. Could you comment on degrees of polynomials and size of constants? In the early examples, I could see the degree of the polynomials was low and the constants were small. But as you got more esoteric, I lost the ability to do the estimate on the fly. Okay. So about esoteric, that's a matter of taste. But regarding the complexity, so as I said, some of the there are these general results where the complexity is not even the constants, the polynomials. They're very high dependence. Here, for example, if I try to think about the result here about the sample base, I think that we can, if we nail down the constants, I think they won't be too high. And actually, I gave also the degree of the polynomials. They were quadratic, and I said 1 was necessary. The 1 over delta was necessary to be 1 over delta squared. The K I do not know, but the constants I don't think are very high. But we didn't. I must confess we didn't. And also the tilde by tilde is just, I think, 1 log factor. And let me think also in the connectivity I gave, and so in both of them actually the constants are pretty good. And I think the place where things are kind of, and that's one of the things that I think would be great to understand, these general transformations, and and I think it's great that we have these general transformations. Can we get even something better than that? So I think that would be a nice. But the other places actually, the kind of the constants and degrees were not. We're not too high. Thank you.
So let's thank Dana again.
Thanks.